Hi, welcome back to the additional content series for the Conquest of Space course. Over the past few weeks, we have been looking into the technologies and ideas that would lead to an increased human presence in space. While space exploration is in itself an admirable goal and scientific endeavor, much of the current development of the space industry is driven by commercial trends. This week, you've learned about present activities like communication satellites or global navigation systems. However, many entrepreneurs are searching for new opportunities and niche markets to explore. One of these potential markets is space mining. Space mining refers to the procurement of resources in space for use within the space infrastructure or on Earth. The main interests, in terms of exploitable resources, are water, which can be used for habitation purposes or separated into hydrogen and oxygen through electrolysis and then used as rocket fuel, and metals, in particular the platinum group metals, due to their high value in commodity markets back on Earth. These resources could be locked in some of the almost 14,000 near-Earth objects, also known as NEOs, discovered to date, 90% of which were discovered after the year 2000. NEOs are those bodies in the solar system whose orbits bring them to within a maximum of 1.3 times the distance from the Sun to the Earth, and they are made from a wide variety of materials, including precious water and metals. At this point, you might be wondering whether it is actually feasible to exploit resources from NEOs or not. For supporters of the space mining, it all comes down to the energy rationale. Their case is made by looking at the delta V's required. Access to low Earth orbit, or LEO, has a delta V of around 10 kilometers per second. For comparison, reaching one of the closest NEOs out there and then returning to LEO requires a total delta V of around 5 kilometers per second. The energy cost comparison is made in terms of delta V squared, as you can see in the image on screen now. However, the difference between these tasks become more apparent when looking at the mass ratios for the rockets tasked with achieving these delta V's. This happens, as you already know, because of the exponential nature of the rocket equation. For example, the trip to LEO implies a mass ratio of payload to initial mass of 33, average for existing launchers. In contrast, the 4 kilometers per second delta V trip to a NEO, loading a mass of mined materials equivalent to that of the spacecraft, and returning on a 1 kilometer per second delta V maneuver would imply a ratio of return payload to initial mass of around 6. Even if this is a slightly ideal value, remember that the main cost in rockets is that of the fuel. In conclusion, it is much more efficient to ferry mass around space than it is to bring it up from Earth. Even so, is there an actual market for space mining today? Well, in the case of rare metals, one would think that this is the case. For example, looking at platinum alone, the global market demand in 2015 was valued in around $6,000 million, with production not fully meeting demand. By comparison, a single asteroid like the famous 3554 Ammon, discovered in 1986, is believed to contain around 1,000 times more platinum than what is produced yearly on Earth. In the case of water, the biggest interest is in the production of rocket fuel in space. In-space refueling stations are typically compared to the railroad during the North American westward expansion, in the sense that they could open the way for a much larger human presence in space. Even without the large space infrastructure associated to the space economy, a potential market for space-sourced water, or hydrogen-oxygen delivery, already exists. There's also one main advantage. About 50% of the mass contained in NEOs is believed to be made of water. For example, the International Space Station receives about 1,500 kilograms of water every year. An additional 3,500 kilograms per year of rocket propellant are required for reboosting of the ISS orbit. At a cost of about $30,000 per kilo to the ISS, that's $150 million per market. Perhaps even more incentivizing is the delivery of rocket fuel to the almost 500 active orbiting geosynchronous satellites. Most of these satellites are commercial telecommunication satellites, which play a part in an extremely profitable market back here on Earth. However, they require fuel for station keeping, and when the fuel runs out, they are cast into graveyard orbits. Telecommunication companies would rather pay for refueling their satellites and extending their operational life instead of having to send new ones. Indeed, a precedent for a $280 million contract to refuel 5 geosatellites already exists. The use of platforms with electric propulsion, on the other hand, which generally requires less amount of propellant, might offset the potential gains of this market. Okay, so the energy rationale makes sense, and there is a potential market for space mining. But we should also mention the large number of challenges that stand in its way. First, it is one thing to detect the presence of NEOs, and a different thing completely to survey them for their potential resources. Remote surveying from Earth using in-space telescopes is possible, but limited in the amount of data that may be gathered. Close surveying will then be required, but this will entail high entry costs. For example, the Near Shoemaker mission and the first Hayabusa mission, both targeted NEOs, had a cost in the range of $250 million and took more than 3 years to reach their destinations. A second set of challenges are related to in-situ operation. Asteroids are very low gravity environments, and thus landing on them is not possible in the same way that it was on the Moon, for example. This means that any spacecraft hoping to attach itself to an asteroid will need to somehow log onto its surface, which might turn to be considerably difficult because of the porous nature of these celestial bodies. Philae, the lander for ESA's Rosetta mission, for example, was equipped with harpoons and drilling screws in order to fix itself to the surface. Finally, as Philae and other probes have been able to confirm, the surface topology of space rocks in general might be highly irregular, making landing and approximation a very difficult task. Of course, none of these challenges actually matter if you cannot extract the resources you plan to mine, and currently there is no dedicated technology which would allow us to do this. The most plausible proposal at the moment would be for the capturing of water, melting it from ice contained in the asteroid and hoping to resolidify most of it on a cold shell around the asteroid. Of course, all of this is still science fiction. In terms of returning material back to Earth, the technology is certainly there. The Dragon capsule by SpaceX can return up to 3,000 kilograms from LEO, and current developments into inflatable heat shields like NASA's HIAT or ESA's IRDT will surely expand their capabilities and lower the cost for recovering material from space. Nevertheless, the challenges mentioned here have not deterred interest both from governments and commercial enterprises in the matter. In November 2015, US President Barack Obama passed the Commercial Space Launch Competitiveness Act of 2015, which would allow, under US law, for individuals or companies to profit from materials found on the Moon and asteroids. Trailing this milestone, Luxembourg announced in February 2016 its intention to create a legal framework to regulate ownership of materials extracted from NEOs, and even to invest capital in some of these ventures. Supposedly, government regulation in the matter would allow for renewed investment in the 2 registered companies which, as of today, have expressed their intent in making space mining a reality: Planetary Resources and Deep Space Industries. Partnership with big names like Google, Virgin Galactic, or James Cameron are already paving the way for a successful start for these ventures. The future of space mining is, in any case, quite uncertain. Water or rocket fuel procured in space might have a larger potential market if we were closer to the dream of a space economy. As of today, however, the investment might only be break-even, and that's without taking into account whether the technology required may actually be developed in a not-too-distant timeframe. As for rare metals, flooding global markets with increasing amount of these materials would significantly drop their prices, going against the very reason behind this endeavor. Some detractors also argue that it would send a potentially dangerous message to the drive for a more sustainable global economy. Thank you for joining us today, and remember to log into our forums to discuss future possibilities for niche markets in space.